Recording. So as you can see, we talked about this. Now let us see that, or let's consider the Navier-Stokes equation. That is the equation that is most common, and most of you are actually familiar with Navier-Stokes equation. So let's do the Navier-Stokes equation for incompressible flow with constant viscosity. Okay. So in a gravitational field. So assume that there is a length scale. Length scale is equal to L, and then there is a velocity scale that is equal to V naught. Can be identified. This is like the characteristic dimension of the boundary and the average of the free stream velocity. Okay? So something like the dimension of the system is a good length scale to begin with. For example, if you have flow through a pipe, then this is the good dimension of the velocity. This can be like the average velocity in the case of wall-bounded flow, or it can be also the free stream velocity in the case of, say, flow over a flat plate. Okay. In this case, flow over a flat plate, the dimension L is basically the appropriate length scale. Okay. So you non-dimensionalize all distance and velocity components by their corresponding scales, and time is made non-dimensional by the reference, by the time scale. So time scale is, say, L divided by V naught. Okay. And pressure variation is normalized by the reference pressure value. The pressure is normalized by, say, E naught, which is the reference pressure. Okay. So this is like the time, the non-dimensional time, tau or T star, say, for example. Okay. So if you now denote the dimensionless variables using asterisks, one can express this Navier-Stokes equation like this. There is d star ui star divided by d star star equal to gl divided by v naught square gi r minus v naught divided by rho v naught square r by dx r plus mu divided by v naught L equal to, this is the second derivative, this one, r square plus square ui star divided by x2 star square plus square ui star divided by dx3 star square, where I is equal to 1, 2, or 3. Okay, so the dimensionless coefficients on the right hand side have been identified as certain numbers. We will see what those numbers are. So this is like a dimensionless velocity Navier-Stokes equation. This is the momentum equation basically, right? So all these coefficients that you see on the three terms on the right hand side, let me mark the coefficients. One is this, one is that, okay, and the other one is this. This particular term is called the Froude number. This particular term that you see over here is called the Euler's number. And this one is called the Reynolds number. Okay, so this is what you get after you non-dimensionalize everything. Pops out a few numbers. Okay, so the Reynolds number, let us see one by one. So the Reynolds number, look at Reynolds number. So Reynolds number is basically rho Vd by mu. V is the characteristic velocity, which was in this case V naught. You can define it in different ways, and mu is viscosity. In case you guys are not aware of this. Then, of course, the other non-dimensional terms will be Mach number. So the Mach number is basically m is equal to v by c, where c is the speed of sound, and v, what you see over here, is actually the fluid velocity. Okay, so it is the ratio of the inertia versus the elastic forces. Then you have the Euler number, okay, which is basically, you can call it C. So it is also you can call it, basically, let's call it Euler. E minus P ref divided by half rho V square. Okay, P ref is basically a reference pressure. It represents the ratio of pressure and inertia forces. Ratio of pressure and inertia forces. And P is basically a reference pressure. Okay, so some of you, it can be also defined as half of the pressure coefficient. So you can call it the pressure coefficient also. Then, of course, there is the drag coefficient. Okay, the drag coefficient. The drag coefficient is written as CD, is effectively equal to FD divided by half rho A V square. So FD is the drag force. Okay, and A is the frontal area. Yeah. Okay, so for example, when you actually have a body and there is a flow around it, so it is that frontal area. So it sees, basically, if it's a sphere, it sees it sees basically pi r square of the sphere as a frontal area. Okay, so that is the area that it actually sees. So you have these flows, and then of course you have the lift coefficient. Lift coefficient. Okay. The lift coefficient is CL is equal to FL. This is the lift force divided by half rho AV square. Okay. So that is the lift force that you can see. Right? It represents the ratio of the the ratio of the lift force and the inertia force. So this is the lift coefficient. Then you have Prandtl number. This surprisingly is not a flow property anymore. This is the ratio of two properties. So it is basically given as mu, as it. Okay, let me write it probably Cp into mu by K. So this is called the the Prandtl number. It is the ratio of basically the momentum diffusivity divided by the thermal diffusivity. Okay? But then you have something called similar to Prandtl number. Again, this is a number which is a ratio of two properties. It's called the Schmidt number. Schmidt number is the ratio of, it is written as SC, is the ratio of this by C, which is C is the molecular diffusivity of, it is the molecular diffusivity of species. Diffusivity of a species. And this one, the one that you see on the top, is basically the thermal diffusion. It's basically the momentum diffusion. Okay? This is the momentum, the kinematic viscosity. So that is what you get over there. So this is the kinematic, like the diffusivity of kinematic viscosity. Okay, so that is the Schmidt number. You have the Froude number. Froude number. So the Froude number is basically Fr. You can write it in whatever ways you want. Is by GL. So it represents the ratio of inertia to gravitational forces. The inertia by gravitational forces. Okay, so it basically is applied to free surface fluids. Then, of course, you have something which is called the Weber number. This is also very routinely used in droplet breakup, for example. So Weber number is rho v square L by sigma. So this is the ratio of inertia to surface tension. This actually tells you how the droplet actually, for example, a droplet like this, whether it will become, like this, deforms. If it deforms, so that would mean that its inertia is high compared to surface tension. Surface tension tries to bring things back. Inertia tries to deform it. So Weber number is basically that. Then, of course, you have the capillary number. Okay. So this is routinely used in the case of droplets, for example. The capillary number, Ca, is basically equal to mu v by sigma, which is a ratio of Weber number by Reynolds number. This is the ratio of viscous forces to surface tension. Viscous to surface tension. Okay, so there is no, inertial effect in that way. Then you have the cavitation number. Okay, so what is a cavitation number? Let's call it sigma c. Sigma c, it is basically P minus P naught divided by half rho V square. So PV is basically this is basically the vapor pressure. Okay. So, and then lastly, you have the Nusselt number, or last few basically. Nusselt number is related to heat transfer, as you know that it is HL by K, where H is the overall heat transfer coefficient. Overall heat transfer coefficient. Okay. K is the thermal conductivity, okay. And so that is what it represents the ratio as. Then you actually have the Biot number. Okay, the Biot number, which is given as Bi is equal to HL by K. The Biot number is H is the overall heat transfer coefficient from the solid surface to a fluid, and K is the thermal conductivity of the solid. So maybe we should put it as S. Okay, so it represents the ratio of heat transfer rates to the surrounding fluid and the solid interior. Okay, and whereas Nusselt number basically represents the ratio of the total and the conductive heat transfer rates in a fluid. So these are very different. Then you have something called a Peckley number. You see that the large gamut of numbers that you see. Peckley number is basically VL by gamma, which is the kinematic viscosity, which is Reynolds number into Prandtl number. It represents the ratio of heat convection and conduction. Okay. Then you have the Grashof number. Grashof number. So the Grashof number is represented as GR, is alpha G L cube delta T divided by gamma square. So this is the alpha is basically, now this is a thermal expansion coefficient. Expansion coefficient. Delta T is the temperature difference. Okay, it represents the ratio of buoyancy forces to the viscous forces. So it's a ratio of buoyancy forces to viscous forces. All right. So then you have the Rayleigh number also. Rayleigh number, which is basically looks pretty similar like a Grashof number. So this is L cube into delta T by gamma and the thermal. So it is gamma by that. So it is basically Grashof into Prandtl. Then you have the Marangoni number. Okay, so the Marangoni number is two Marangoni numbers. If you write it d sigma by dc, so you can see it is the, and then dc by dx, okay, into L square, okay, and then you divide it by mu E. So this is for concentration gradient. You can see what it is. It is the rate of change of surface tension with composition and the composition gradient across the length. And this is multiplied by the characteristic length scale. Okay, so this is for concentration gradients. And then you have the Marangoni number. And this is very important, for example, in droplets and in other flows also. And this is, for example, this is with respect to temperature, mu gamma. So this is now divided by the thermal diffusivity. So this is for temperature gradients. All right. So then you actually have something which is called Richardson number. Richardson number, which is basically Ri is equal to, is basically minus fluid number half. It represents the ratio of potential energy associated with gravity and kinetic energy. Okay, so that is the Richardson number. Then you have the Taylor number for rotating flows. And this is also very common, the rotating flows, because fluid dynamics is something like that. So this is the Taylor number, which is given as gamma square, omega square rather, square of that. So this is basically what is called the rotation rate. Similarly, you have other numbers. For example, let's talk about one Strouhal number. Strouhal number, it's like shedding of vortices behind bluff bodies. So like this. So if you have a bluff body here, behind the vortices are shed. So this frequency of shedding is what comes here, and this is the characteristic length, this L, and this is the corresponding velocity, say V. So this is the Strouhal number. You can have something called a Knudsen number also. Knudsen number, which is basically represented as lambda by L, where lambda is basically the mean free path. Okay, and L is again the characteristic length. So you have lots of numbers like this. When you actually use these numbers for non-dimensionalization, these are accepted numbers, so to say. So this has got its own utility. So apart from this, the fluid also has many patterns. Okay, and flow visualization and measurement methods provides images or records of the fluid or the transported mixtures, and it gives you information on the flow. So the correct interpretation of the observed patterns, it is necessary to understand their relationship with the actual flow characteristics. So for example, we image patterns, and how these patterns are linked to the flow characteristics, to the actual flow characteristics. This is important, okay? Because we image patterns, or we measure patterns. Okay? So you can see, for example, you get all these kind of flow velocities, you can get all kinds of vector fields around it. How is it linked to the actual flow characteristics? So there are ways, for example, if you look at, you can take an instantaneous position of a fluid particle or marker provided by a still camera with a short exposure time. So you can determine the instantaneous position of visible. This can be introduced by dye or tracers, the fluid parcel, or marker provided by a still camera with a short exposure time. What is exposure time? We will learn later. Exposure time, but assume that this is a short exposure time. You know what you are trying to do. And then, so this is the instantaneous position, for example. Similarly, you can determine something like a path line, okay, which will be the locus of the positions of the fluid particles during a time interval. So this is a fluid particle that is moving around. So this is at t equal to t1. This is at say t equal to t1 plus some t interval. So this is the locus of a fluid, locus of the positions of the fluid particle, locus of the positions of the fluid particle during a time interval. Okay. Then you have something called a streak line. What is a streak line? So the streak line is the locus of all fluid particles that have passed through a fixed position in the fluid during some time intervals. So it is basically the locus of all fluid particles, okay, that have passed, okay, through a fixed position, fixed position, in the fluid, okay, during some time interval. So all these are processes that you can measure them, right? So this is called a streak line. Okay? And then you, of course, have a timeline, namely the locus at a given point of all the fluid particles. The combining of the preceding patterns, the time streak lines, or photographic exposures, you can determine many things. Okay. Then it is also important to understand that all the preceding patterns are distinct from the instantaneous streamlines. Okay. Namely lines in the fluid which are tangent at all points to their local velocity vector. If you know that the streamlines, okay, are given by something like this, 1, x2, u2, please consult your fluids notes. Okay, so in steady flows, okay, you know, path lines, okay, streak lines, and streamlines coincide. This is also something that you know already, probably. Okay? But in unsteady flows, they may be different. Flows, they are different. Okay? The streamlines where the flow velocities are tangent at each point. Okay? So you see, so in stationary or turbulent flows or relatively low intensity, these lines may approximately coincide on an average, but their instantaneous features are different. So one may reconstruct a set of streamlines in unsteady flows by fitting a family of tangent curves to an image of many short path lines generated by adjacent particles, and thus representing the vector velocity field. So this is interesting. So you can say, you can reconstruct, because you need the streamlines, right? Reconstruct a set of streamlines, okay, in unsteady flows, okay, by fitting a family of tangent curves, okay, to an image okay, of many short path lines. Many short path lines generated by particles. And therefore, you can generate the velocity vector field. Because our aim is to form the velocity vector field, because this is what is then going to be used for calculating vorticity, acceleration, stress, etc. Okay? So this is the most important thing, that you need the velocity vector field, and that you can do from the images in a varieties of ways. Okay, varieties of ways you can generate these kind of images, and that is the most important part. So this is what a very short description of fluid mechanics is all about, where we have considered all kinds of flows. We have considered what are the key features of the flow and how to non-dimensionalize a particular quantity, and how to non-dimensionalize an equation and come up with the predominant scales, and how, if you get an image, if you get a measured data, how you can generate these non-dimensional numbers and get more insights into the flow field. If you are talking about velocity, that is essential for a whole lot of derivative quantities. Similar thing, you want temperature, that can be now utilized for a varieties of things, including calculating the rate of heat transfer. Okay, so we end the lecture here.